So I'd like to thank you all for coming tonight. My name is Brian Conrad. I'm a professor in the math department, and I'd like to say a few things about this evening's speaker before he starts. Benedict is certainly one of the most prominent number theorists in the world, and among his many honors, he's won a MacArthur Genius Award, and he's also a member of the National Academy. And so tonight, we're very happy to have him to tell us about solving cubic equations.
Thanks very much, Brian. It's always embarrassing when you speak and the person who introduces you is better presented than you are. But I'm gonna try my best. So this is a talk I put together with a collaborator, William Stein, who teaches at the University of Washington and is responsible for writing a terrific computer language now called Sage. And William gave this talk at the AMS meeting, and I gave a similar talk in Mumbai about a month ago, and a very responsive audience, so I'm going to see if you guys are just up to scratch with the people in Mumbai. So when you do mathematics, there are really two types of equations, and when you choose which area you're going to work in mathematics, you have to choose which kind of equations you're going to solve. So the first type of equations are algebraic equations, and one of the most famous algebraic equations was discovered some time ago, and it's the relationship between the side lengths of a right triangle. That if A and B are the two sides and C is the hypotenuse, you have this famous algebraic equation between their lengths. And we like to attribute this theorem sometimes to Pythagoras, but and here's a bust of something that's supposed to be Pythagoras, but you shouldn't take that too seriously because no one actually knows what Pythagoras looked like, and in fact, no one actually knows if a man named Pythagoras actually lived. He may have been a creation of the Platonists who sort of liked the idea of his school, but if he did live, it was about 600 BC. In any case, he didn't discover this. When I was in India, my friends pointed out that it appears already in a sutra of Baudhayana, which is 800 BC, and in fact, we're going to see that the mathematicians of Mesopotamia knew about this about 1,000 years earlier than that. In any case, this is one of the most famous algebraic equations, and we're going to come back and study its solutions. And the other type of equation you can solve if you're a mathematician is a differential equation, an equation that relates the change in a function to the behavior of the function, or its derivatives to the function itself. And if you solve algebraic equations, that's called number theory. And if you solve differential equations, that's called analysis. And you have to pick one of those two if you're going to be a mathematician. And this is pretty much the most famous differential equation that there is. It says that the derivative of the function is equal to the function, value of the function. It's called the exponential differential equation. And if you know what the initial value of the function is, and the value of the, let's say the initial value at time t is 0, is 1, then one of the great results is that there's a unique solution of this equation, the exponential function, and it was discovered in the early days of calculus that this had an expansion as an infinite polynomial, or what we would call a power series, and could be fairly well approximated by this power series for small values of t. And this differential equation occurs all over applied mathematics. There's so many situations, the growth of bacteria, the growth of populations. So when I gave this talk in Mumbai, I illustrated it with the following example of exponential growth. This is the graph of the population of India. And you notice that since 1950, when they had an adequate food supply, the population of India has been growing exponentially. In Mumbai alone, there are 13 million people who are essentially homeless. So this is something that we're going to have to deal with in the future, but we'll go back to algebraic equations for the moment. So even though we don't know if there's someone named Pythagoras, we have a wonderful concept in number theory called a Pythagorean triple, which is a solution of this equation, sides of a right triangle and the hypotenuse, A, B, and C, where they're not just real numbers, the lengths that can be the lengths of a triangle, but actually integers like 3, 4, and 5, and 5, 12, there it is, 5, 12, and 13, and 7, 24, and 25. Those are collections of solutions of this equation where A, B, and C are whole numbers, and those solutions are called Pythagorean triples. And in fact, I'm going to show you that there are an infinite number possible of Pythagorean triples. I'll show you the most general solution of this equation, And we think that the most general solution was known to the Babylonians almost 4,000 years ago. And the reason we think this is that there's a tablet that now sits in the archives of Columbia University that lists these solutions of the Pythagorean triple equation. This tablet was deciphered by the great mathematical historian of our century, Otto Neugebauer. And we don't know why this tablet was written. We don't know what else is on this tablet, but the suspicion is that if they could find this many distinct Pythagorean triples, they may have known the general form of it. Neugebauer speculates that the mathematics in the height of the Babylonian Empire was about the same level as the mathematics of early Renaissance Europe. Just an amazing achievement. Well, let's find the general solution, and we can imagine perhaps how they did it. We'll use a little geometry. So if we're trying to solve this equation when a and b and c are whole numbers, we can make the rational numbers by dividing by c. Of course, the hypotenuse will be longer than the sides, so the rational numbers x, which are a over c, and y, which are b over c, are rational numbers between 0 and 1. And they satisfy the equation that x squared plus y squared is equal to 1. So instead of looking for integer solutions of the original equation, we'll look for rational solutions of this equation, which has only 2 variables. And of course, we study in geometry that this is the graph of a circle. And those points that are marked in blue in the plane constitute the real solutions of that equation, where x and y are both real numbers. And we have to find which points on the circle have x and y both rational numbers. And if they're both rational numbers, then clearing the denominator of c, we would get integer solutions of the original equation. So here's how you can do this. Connect a point on the circle, x and y, to the other point on the circle, which is the point minus 1, 0. And that line goes through the y-axis at a certain point. Call that point 0, t. Now, t is clearly determined by x and y, because there's a unique line through these 2 points, and it meets the y-axis at some point, and so that x and y must determine t. But conversely, if I know what t is, I can solve for x and y, because I take the unique line that goes through the 2 points that are marked black on this diagram, the point minus 1, 0 and the point 0, t. That meets the circle in one more point. And putting that linear equation into the quadratic equation, I can solve for x and y. And when I do that, I find the following formulas. The t, which you can get very easily from the slope of that line, is y over 1 plus x. And slightly more complicated, that x is given by this expression in t, and y is given by that expression in t. So, as I say, there has to be some formula, and when you work it out, it's this formula. Now, here's what I want to observe. That if x and y are both rational numbers, namely of the form a over c and b over c, then t is also a rational number. But on the other hand, if t is a rational number, a quotient of 2 integers, then so is t squared, and so is 1 minus t squared, and so is x, and so is y. And so this geometric map, by taking the line through the points, gives us a complete correspondence between the rational solutions of this equation that we're looking for and the rational points on this line that lie between 0 and 1. And it's easy to list out rational numbers. We just write the number t as p over q, and we solve for what x and y are, and we find that x and y are given by these expressions in p and q. And remember, we're supposed to clear the denominator. So clearing the denominator, we find that a and b and c are given by these expressions in p and q. And you see, p and q are both integers because t is a rational number, and so this gives us an integer solution of the Pythagorean equation. And in fact, it's the most general integer solution of the Pythagorean equation. And so if you take, for example, t as a half, you get that solution 3, 4, and 5. And you take t as 2/3, you find 5, 12, and 13. T is 3/4, 7, 24, and 25. And all the solutions that are on this amazing tablet correspond to small rational values of t. And so perhaps, we'll never know because we don't have enough information to reconstruct most classical mathematics, perhaps the Babylonians had this method and found the general form of the solution. Here it is. So that's what I wanted to tell you, just to warm you up. That's about quadratic equations. And in one sense, quadratic equations were well understood by the mathematicians of antiquity. The classical mathematicians of Greece had divided the different conics, the ellipses, the parabolas, the hyperbolas that we study in high school, and they also knew how to find integer and rational solutions of quadratic equations. But what I want to talk about today are cubic equations. Quadratic equations are when one of the terms has an x squared in it, or a y squared. Cubic equations, they raise the power to the third degree. So a very famous cubic equation, analogous to the circle, is the first, x cubed plus y cubed equals 1. That was studied by Fermat. Let's see if I have a picture of Fermat. There's an actual picture of Fermat. Fermat was a great number theorist who lived in the 17th century and was fortunate to obtain a translation of the work of Diophantus of Alexandria, which had been translated first into Greek and then into Latin. And then Fermat began his work. He was a lawyer in Toulouse. At the time, no one was a professional mathematician, but he corresponded with the great savants of Europe. He had a long correspondence with Pascal. It was a shame, in fact, that he couldn't persuade Pascal to write up his work because he had developed a number of amazing methods to study cubic equations. But he left behind at least some hints of what he had in mind, and that was picked up by Euler, the great mathematician of the 18th century who developed his methods. Now, the difference between quadratic equations and cubic equations is quite profound. In quadratic equations, like the circle, we found that there were an infinite number of rational solutions, an infinite number of values x and y that satisfied the equation. But cubic equations, some have an infinite number of solutions, which are rational numbers, and some have a finite number. So for example, for the first equation here, there are only a finite number of solutions. Fermat claimed that himself, and Euler gave a proof. And the only solutions are when x is 1 and y is 0, or when x is 0 and y is 1. So only two solutions there. However, the second equation has a large number, in fact, an infinite number of rational solutions. An obvious one is when x is 0 and y is 0, also when x is 1 and y is 0, and we're going to see a way of propagating some solutions into more. And that was what Fermat essentially discovered. And the remarkable thing about cubic equations, as distinguished from all other equations in two variables, quadratic, but also equations of higher degree, fourth and fifth and sixth degree equations, is that there's a method of going from two known solutions to a third. And the method is geometric, just like it was in the case of the quadratic equation. So here's a graph of that second cubic equation that I've done for you. The blue are the real solutions of the equation. And suppose we start with two solutions indicated on this oval over here by those 2 points, and we take the line that goes through those two solutions. Well, since it's a cubic equation, the equation of a line is y is some multiple of x plus another number. And if you put that into the equation, you get a cubic equation in x. And that means that it meets this graph in 3 points, namely, starting from these 2 points and taking the line through it, it meets the curve in a unique third point. In the quadratic equation, a line met the curve in 2 points, but for a cubic equation, it meets it in 3 points. And the remarkable fact is that if the first 2 points have rational coordinates, so does the third. So that we can propagate two rational solutions into a third. Here I have the two solutions, minus 1, 0, and 0, minus 1. When I take the line through it, it actually meets it in an integer solution, 2, minus 3. Let's move this away. Okay. And that is what really distinguishes cubic equations, which are now called elliptic curves, from all other curves, that there's a method of taking known solutions and producing new ones. And this is what Fermat discovered. And you see, taking this line between 2 points is called a secant line. If you let the 2 points come closer and closer together, then the secant turns into a tangent line. Fermat knew this. He was one of the early developers of calculus. So here's an example where we start with the point 2 minus 3 that we've produced from the previous 2 points. We take the tangent line through that point. that meets the curve twice at this point, and it will meet it at one other point, and there's a new rational point that we've constructed. And so from these initial points, you can do this secant and tangent process and hopefully construct many more solutions. And the solutions quickly become quite large. So here is this curve I've been discussing, and we start with these very small solutions, then we got that solution 2 minus 3, and we keep drawing the secant line through the previous one and seeing where we hit. And you see we get rational numbers, but the rational numbers are growing quite rapidly. And in fact, one can prove that for this specific cubic equation, this process continues, and there are an infinite number of rational solutions. Each iteration of the Fermat process of taking the secant line and finding the next point of intersection gives you a larger solution. You never come back to where you started initially, and so that produces an infinite number of solutions. And the main question really that we still don't know how to solve completely for cubic equations, it's amazing that such a classical question is still at the forefront of mathematics, and it is, it's a central question in number theory, is when, if I'm given a cubic equation, does it have a finite number of solutions, and when does it have an infinite number of solutions? I mean, that's really one of the millennial problems in mathematics that's being offered by the Clay Institute. Now, I should say that in this case, we proved there are an infinite number of solutions because the first few solutions were easy to guess from the equation, and we just continued with this secant process. But the simplest solution of an equation can be quite large, and you don't want to just go looking mindlessly for it on the computer. So here's an example of a cubic equation where the coefficients are not terribly large, 10 or 15 digits, and the simplest solution, this is just the x coordinate. This is not the y coordinate. The numerator has 5,000 digits, which you can't see, and the denominator also has about 5,000 digits, and that is the simplest solution. They're an infinite number, but this is like the solution 0, 0 on the previous curve, where you can take the tangent line through this solution and produce a much larger one. But someone had to have some kind of systematic way of constructing this solution, and in fact, the person who found it, Mark Watkins, did. You can't find something this large by a computer search. You'd be searching for a very, very long time. Now, I'm going to define the invariant that, as number theorists, we like to use for a cubic equation called the rank. And I can't give it to you exactly because I'm working within the boundaries of this lecture. I'm not supposed to use too much mathematical terminology, but it's essentially the number of independent solutions, namely the number of solutions you have to find such that by applying this process, you get all of them, the chord and tangent process. So for example, if the rank is 0, that means there are only finitely many solutions. And if the rank is positive, that means there are infinitely many solutions. So we're really trying to decide if the rank is 0 or positive. On the other hand, there is a difference between rank 1 and rank 2 and rank 3. There are more and more solutions if the rank goes up. So for example, this very simple equation, when you take a equals 0 or 1 or 2 or 4 or 16, you get cubic equations with different ranks, 0, 1, 2, 3, and 4. So looks similar equation, but the first one has only finitely many solutions. The second and third and fourth and fifth have infinitely many solutions, but there are more solutions as you go along because you need more to construct different solutions to be able to generate them all. Now, the main theorem in the subject, which was proved about 100 years ago, this rank is always finite. Namely, you only need a finite number of solutions to generate them all. For example, in this crazy example, this single solution generates all solutions under this chord and tangent process. And this theorem about the rank being finite is called the Mordell-Weil theorem. It was proved initially in this situation by Louis Mordell, an very, very proper English mathematician who was actually born of Lithuanian immigrant parents in Philadelphia, and André Weil, one of the great mathematicians of the 20th century, who wrote his PhD thesis in Paris generalizing Mordell's result. And even though it's finite, we know very little about it. For example, are there equations where the rank becomes arbitrarily large? We've given examples where it's 0, 1, 2, 3, and 4. Can it be 5? Can it be 7? Can it be 1,000,000? Can it be as large a number as you want? And we don't know. And the current record is 28. And that was found by my colleague, Noam Elkies, who's sitting at the piano. He's also quite a composer. And it's this cubic equation with rather larger coefficients, as you can see. And these are the 28 independent points. In fact, x and y are integers for this equation that Elkies found that he can prove are independent and probably generate the rank. And this was found about 5 years ago. There was a process on computer searching, very intelligent process of computer searching for these equations, where people first made rank 12, and then a couple of months later made rank 13, and then made rank 14. And this was all going very well, and I think most of us at the time felt that with enough computer power and enough cleverness, we could see that the rank was going to infinity. But it ground to a halt, and this curve was found about 5 years ago, and no one's been able to improve it. So right now, people are agnostic as to whether the rank goes to infinity or not. So I'm going to tell you about an amazing conjecture that was made 50 years ago, which dominates the subject, called the conjecture of Birch and Dyer, which is this famous problem of the Clay Institute. And most work that's gone on cubic equations has been about this conjecture. And here's a picture of Brian Birch is on the right, and Peter Dyer is on the left. This is the day that Birch is getting married. They're both now distinguished mathematicians in their mid-80s. And Dyer was his best man. And I use this picture to indicate that very frequently in mathematical collaborations, you make very good friends. And these two became wonderful friends. They had a brilliant idea to try to guess the rank, the number of solutions over the rational numbers that were needed, based on the average number of solutions of an equation at a prime number p. So to tell you what their conjecture is and what people have done on it, I have to tell you a little bit about prime numbers and what it means to solve an equation at a prime number p. So people usually know a prime is a number greater than 1, not divisible by any smaller number. So the first few prime numbers are 2, 3, 5, 7. 9 doesn't work because it's divisible by 3. 11, 15 doesn't work. It's divisible by 5, etc. And Euclid, one of the great theorems in Euclid is that there are infinitely many primes, but it's a non-constructive proof. And so this sequence of prime numbers goes on forever, and it's been quite challenging using the computer to try to find larger and larger explicit primes because there's no known formula that generates prime numbers. And the largest number that's been found so far is a Mersenne prime, a power of 2 minus 1, which has 12 million digits. I'm going to give you an idea of how large that is in a second. But one thing that's very surprising about prime numbers is that they have a very regular rate of growth. So these are the number of primes less than 500, where you see it's a sort of a jagged function, but growing at a regular rate, even though we don't know when the next prime will appear. And so this regular rate of growth was noted by Gauss at the beginning of his mathematical career and is now known as the prime number theorem. And it says essentially that if you grab a number at random, then the probability of it being a number of size x at random, the probability of it being prime is 1 divided by the logarithm of x, the natural logarithm of x. Essentially, your probability is 1 over the number of digits. Well, the number of digits multiplied by 2.3. So you have quite a good chance of finding prime numbers. Here's an example of a prime. This prime has 3,000 digits. That's a very small prime. So to give you an idea of the prime number that has 12 million digits, take each digit of this number and replace it by this screen of digits. And then you're getting up there. Then you're getting up near 12 million digits. And I did an art exhibit in Paris a year ago with a wonderful Japanese installation artist named Ryoji Ikeda, where we exhibited 2 numbers of 7 million digits. One was randomly generated, as much as a number can be randomly generated. And the other was a Mersenne prime of this form with 7 million digits. And the numbers were printed on a piece of paper that was about this wide and ran from that door to this door. And the numbers were 3 pixels wide and 5 pixels high. So you need a magnifying glass to actually see them. I went to the Mersenne prime and actually checked the last 400 digits so that I was sure that Ryoji wasn't just fooling everyone. And the amazing art project was to how you print this out. He got a special grant from Hewlett-Packard, et cetera. And it was a mind-boggling experience. Many of the great mathematicians from Paris came in to see the exhibit and to look at these numbers. And of course, all you could see were these pages of gray, because you couldn't even distinguish the digits. And how could you possibly tell a prime number apart from a randomly generated number? And the reaction of the mathematicians was very interesting. Many of them were like, wow, this is wonderful. This is what we've been working with. And yet some of the leading ones, for example, Jean-Pierre Serre, probably the greatest mathematician of our time, was like, I don't want to think about a prime number that way. A prime number is a p. If it's any bigger than that, I'll get lost. But it's amazing what the computer can generate now. And well, let's go back. I should say that prime numbers have been enormously interesting to us in cryptography, because it's now known that you can test whether a number is prime very quickly in the same time that it takes essentially to write down the number. That's called a polynomial test. And we knew that experimentally, but it was recently proved in a great paper. Primes is in P. That's the class of polynomial time problems. It's called the AKS test, after three Indian mathematicians who were at IIT in Kanpur. I note that the last two, Kayal and Saxena, were undergraduates at the time this great paper was written. So that's a challenge to all of you undergraduates at Stanford to get to work. They're working quite hard at the IITs in India. On the other hand, if a number fails to be prime, so as a product of smaller numbers, we call that composite, it's much more difficult to factor it. And this fact that it's easy to test for primality but differ to factor a number if you can't prove that it's prime is the basis of many, many public key crypto systems. In particular, the company called RSA, Ravesh Shamir Edelman, has made is the background for many of our credit card transactions on the internet, that they send companies numbers that are products of two very large primes. And in fact, they put out challenge numbers. So this is their 768th challenge number, which has some 300 odd digits in it, and it was recently factored into two prime numbers of et cetera. And this is about the level of factoring we can do now with the most powerful machines and the greatest mathematical techniques that we have. This is about the level of a number that we can successfully factor into two primes. And of course, it's much smaller than these numbers of 12 billion digits that we can prove are prime. And this trapdoor, where it's easier to produce primes and then multiply them together, the poor person who receives the number that's been multiplied together can never split it apart. And that's the basis of a lot of coding nowadays. Well, let's get back to cubic equations, enough primes. And what do we mean in this prediction that was made by Birch and Dyer by a solution of a cubic equation at a prime number p? What do we mean by that? Well, let's take our favorite equation. Y squared plus y is x cubed minus x. Now, 0, 0 is an actual solution. Namely, you put 0 on the left-hand side, you put 0 on the right-hand side, you get 0 is equal to 0. But I claim that 3, 1, where it isn't a solution, is a solution at p equal 11. What I mean by that is that if I take the remainder of the left-hand side after dividing it by 11, that's going to be equal to the remainder of the right-hand side when I divide it by 11. So if I take x equal to 3, the right-hand side is 27 minus 3, which is 24, which gives a remainder of 2 when divided by 11. And the right-hand side is 1 plus 1, which gives a remainder of 2. So even that's not a solution. I mean, 24 is not equal to 2, but they give the same remainder when divided by 11. And that's what we call a solution at the prime 11. And it turns out that that only depends on what the remainder of x is at 11 and what the remainder of y is at 11. And so there are only finitely many things to test. In fact, there are only p squared things to test. There are only p possible remainders for x, p possible remainders for y, so p squared possible remainders to check, and each time you put them in the equation and see whether the right-hand and the left-hand side are the same as a remainder. So you can do this in the number of solutions we call AP. And here are two cases where we took the prime to be 23. And of the p squared possible choices, you see there are p
23 choices for x here, 23 choices for y here in terms of remainder. I put a blue dot where you get a solution. And there are 22 solutions out of the possible 23 squared choices. And here's the prime 71, and I take this equation, and I have 71 choices for x and 71 choices for y, and the blue dots indicate where the remainder of this side is equal to the remainder of that side, and it turns out that there are 63 solutions at the prime 71. Now, if you have a solution of the original equation in rational numbers or integers, that certainly gives you a solution at all the different primes p, right? Because if the two numbers are equal, they certainly have the same remainder after you divide them by p. And we usually write the number of solutions as p plus 1 minus ap, because p plus 1 is about the number of solutions you'd expect for a linear equation, and ap is an error term. And we define a function of one variable called the L function of the elliptic curve, or the cubic equation, by an infinite product. So now we're going into the world of analysis. We started in the world of algebra. We're just trying to solve an equation. But we have infinitely many primes p. Remember, that's what Euclid proved. And so for each prime p, we count the number of solutions, get some number between 0 and p squared, which we write this way. And then we make an infinite product, which is similar to other infinite products in number theory, which we can expand out as an infinite series. And wherever this product converges, we get a function of the variable s. And that encodes how many solutions we have for each prime p, all the infinite ones. Now, it turns out that this definition of a function only works when the variable s is bigger than 3/2. In that case, you can show the product actually converges, and you get a well-defined function. It's like a convergence of an infinite series. And so if we graph the function, we could graph it all the way up to the point where s was 3/2, but less than 3/2, we wouldn't have any way of defining it because this infinite product turns out not to converge. Now, the idea of Birch and Dyer is very audacious. They said, well, yes, it's true that the function doesn't converge in this region, but suppose we just put s equal to 1 in this product. That's not a point in this region because s equal 1 is not bigger than 3/2. So the function really doesn't make sense. But if we put s equal 1, we get this infinite product. And when we clear denominators, etc., it's the product over all primes of the prime divided by the number of points. And remember, the number of points was either a little bit above or a little bit below the prime. Now, their idea was, if your number of points is on average large compared to the prime, if it's in general bigger than the prime, then this product would be a product of numbers less than 1, and it will tend to approach 0. And the larger AP is on average, the faster this will go to 0. And why should that be related to the rank? Well, the larger the rank is over the rational numbers, the more solutions I have over the rational numbers, the more solutions on average I would imagine I would find at primes p. And so they guessed that the rate that this product tended to 0 would be related to the rank of the curve. And here's an example with that curve that I said of rank 28 of Nomelke's, where I show you the value of this infinite product as I take the primes less than 100, and the primes less than 200, and the primes less than 300, primes less than 400, primes less than 500. It's going to 0 very quickly. And based on that, they made a formal conjecture. And here it is. So the first thing is you have to have some behavior of this function near s equal 1. I mean, you can't just set s equal 1 in a product which doesn't converge. So the first part of the conjecture is that this function, which is defined for s bigger than 3/2, has a continuation, and I'll say what that means in a second, to a neighborhood of the point 1. The second part of the conjecture is that the order of vanishing at 1, whether the function vanishes or the derivative vanishes or the second derivative vanishes, that's this infinite series at s equal 1 called the Taylor series, is equal to the rank of the curve. So that's a measure of how fast the function is going to 0 is determined by the rank. And even more, they predicted that the leading term in this infinite expansion at s equal 1 is given not just the order of vanishing, which is supposed to be the rank, but the leading term is supposed to be given in terms of some arithmetic invariance of the equation, which I'm not going to define. And the most mysterious arithmetic invariant in this
was studied by the great number theorists John Tate and Igor Shafarevich, who conjectured it was finite, and they called this invariant Shah. Actually, Tate called it Shah, so he could pin it on Shafarevich. That's the Cyrillic letter. And here's a picture of John Tate, my thesis advisor, and Igor Shafarevich about the time they did that work. So you had this conjecture about a function where you didn't even know it was defined in terms of an invariant that you didn't even know was finite. That's very good in mathematics. The more things you don't know, the more things you can play off against each other. So if there was only one unknown quantity here, it would be very difficult. In any case, this conjecture was made and formalized in the 60s, some 50 years ago. So I have to tell you first what an analytic continuation is. And that goes back to the work of Euler. So we know that this infinite sum, it's the geometric series, converges when x is of absolute value less than 1. And there's its graph in the region between minus 1 and 1. But in the region between minus 1 and 1, it's equal to the function 1 over 1 minus x. That's the formula for the geometric series. And this function extends way past minus 1. It extends all the way into this region. So we would say that this function gives an analytic continuation of this infinite series in the region where the series doesn't converge. And that's what one was looking for this function associated to an elliptic curve. This infinite product, see if I can find it. This infinite product that defines the function only converges in this region, but perhaps we can find another formula for the function that will allow us to continue it to s equal 1 and actually try to do the conjecture of Birch and Dyer. Well, that's a great result. And it was proved in the course of the proof of Fermat's last theorem. It was proved by Andrew Wiles and Richard Taylor in 1995. And they proved more than the analytic continuation of this function. They proved that this function that was given by the series, if you replaced n to the minus s by an exponential function, was something called a modular form. One of the great achievements of the late 20th century in mathematics. Here's a picture of Andrew Wiles and Richard Taylor, who collaborated on this result. And as I say, it's the key result that's needed in Wiles's proof of Fermat's last theorem. So, but I think it's much more important in some sense than Fermat's last theorem because it allows us to attack all cubic curves, not just one equation. Well, with the analytic continuation, that's part one of the conjecture, you can talk about the order of vanishing of the function. And combining a formula I proved with Don Zagier in 1983 with some work of Victor Kolyvagin, we can now show the following, which is not the full conjecture, but it's a little bit of progress. We can show if the function is non-zero at 1, the rank is 0. That's what's predicted, so there are only finitely many solutions. And we can show if the function is 0, but the derivative is non-zero, then the rank is 1. So there are infinitely many solutions. And that's how, by the way, that huge solution was found that I gave you earlier in the talk. It was a construction that Zagier and I found for a solution of a cubic equation when the derivative was non-zero. And in both cases, we can also show that the group that Tate and Shafarevich defined is a finite group. So here's a picture of my collaborator, Don Zagier, and here's Victor Kolyvagin. Kolyvagin was a student of Shafarevich at exactly the same time that I was a student of Tate. Each generation in mathematics passes problems on to the next generation to solve. And they seem impossible to us, and then the younger people stop in. I should say that my collaboration with Zagier was a lot of fun. I met him when I was 25, and I was a graduate student in Harvard, and he was 24, and he was already a world-famous mathematician. He had already a position at the Max Planck Institute at Bonn. He got his undergraduate, he got his high school degree when he was 13, and he wanted to go to Oxford very badly. So he took his A-levels and O-levels. He did wonderfully well, but he was told that Oxford took no student as an undergraduate under the age of 16. So he went to MIT. He finished MIT in 2 years. He applied to Oxford to be a graduate student, and they took him at 15 because there was no regulation against taking a graduate student at the age of 15. He got his PhD at 18. As I say, by the time I met him, he was a visiting professor at Harvard. The world is just not fair. But it was great fun to collaborate with him. And this is about where we got to. And when the order of vanishing is greater than 1, so if the function vanishes and the derivative vanishes, so you'd expect that the rank is at least 2. There should be a lot of solutions. We can't prove anything. We can't construct a single solution on the curve. However,
as in many areas of number theory, the computer has been a great guide. And here's a summary of what evidence has been acquired for the simplest curve of rank 2. With this equation, the order of vanishing of the L function is equal to 2. We know that. And most primes up to 50,000 do not divide the order of this invariant SHA. In fact, we think the invariant is a group of order 1, so it should be divided by no prime, but at least you can check it up to 50,000. And that work was done by my collaborator on this talk, William Sage, who's the younger generation of mathematicians who goes flying off things in skateboards, so that's a picture of William. So I'm going to finish this talk by leaving the conjecture of Birch and Dyer. As I say, there hasn't been any real theoretical progress on it over the last 25 years, to describe some very exciting work that's taken place over the last 3 or 4 years, I think a real breakthrough in the subject, on the average rank of elliptic curves. So this is not going to consider one cubic curve at once, but all of them at the same time. And this work is done by Manjul Bhargava, a young mathematician at Princeton. Here's a picture of Manjul. And it also uses analysis, differential equations, infinite series, volumes, things like that, but in a different way. So to talk about the average rank, you have to say how you're going to enumerate all of the different cubic curves. And it turns out that every curve has a unique equation of the form y squared is x cubed plus ax plus b, where a and b are integers, and they're not divisible simultaneously by p to the fourth and p to the sixth for any prime p. And with that unique equation, you can define the height of an elliptic curve or a cubic equation as the maximum of the positive integers a cubed and b squared. And then, if you fix a number x, there are only finitely many curves which have height less than x, because you've bounded a and you've bounded b, and they determine the curve. And in fact, if you call this number n of x, it grows about the same rate as x to the 5/6 power. So it goes to infinity with x, because there are about x to the 1/3 values of a, and there are about x to the 1/2 values of b. Okay? Now, we'll call the average rank this limit, if it exists. We'll take the sum over all the curves where height is less than x. That's a finite number of curves. We'll take the rank of the curve, and we'll divide by the number of curves of height less than or equal to x. And if that limit exists as x goes to infinity, we'll call that the average rank. That's the definition that Manjul uses. And with this definition, I should say that we all now expect that the limit exists and is equal to a half. In fact, we really believe that on average, half the curves have rank 0 and half the curves have rank 1. And the occurrence of a rank 2 or 3 or 4 or 28, as Elke's found, is extremely rare on average. But we can't prove that. What Manjul and his graduate student Arul Shankar have shown is that there's an upper bound on this limit. We don't know this converges, but there's the upper bound on the possible limit. And they've obtained a specific upper bound which is less than 1. And since it wasn't known before their work that this limit was even finite, perhaps the rank went to infinity in a serious way, I think this is tremendous progress. It's not an analysis of the points on the elliptic curve at a prime p. It's a different direction than the conjecture of Birch and Dyer, but who knows? It may be in some way compatible with it, and it's tremendous progress on this question of the number of solutions to cubic equations. So I want to end by thanking you. So here's a picture that was taken of me 40 years ago. I put it in the slide when I gave the talk in India because it was my last visit to India, in fact, and I was a student in Chennai, then Madras, of Carnatic music. One of my students said that I looked like I had achieved nirvana at this point. I had achieved a certain nirvana, namely, I realized when I was studying there how beautiful the tradition was of Carnatic music in India. And I also knew that I wasn't going to be a professional Carnatic musician, but I decided at that time I wanted to try to get involved in a great historical tradition. And I think I hope I've been able to show you that mathematics is a great historical tradition, and those of us who work in the field are just honored to be a part of it. And the problems are extremely challenging. They pass from generation to generation. I hope some of the young people in the audience go on to study more mathematics, and perhaps you'll make the next great advance in the field. So thank you very much.
So we have time for some questions. There are microphones on both sides. If anybody has any questions, maybe a couple of questions if people want to ask.
It was perfectly
Going?
Oh, good.
Yeah. I'll repeat it. Okay, so the question was that if we plotted the solutions in the xy plane, would we see any patterns in the solutions?
Well, I think it's a good question going to this graph of the cubic equation. Let me get there. So these are the real solutions of the equation. And if you plot the infinite number of rational solutions, what we can show is they become dense in the real locus. They're not concentrated in any particular part of it. But at any point in the real locus, if you put a small interval around it, you'll find infinitely many rational solutions. So they distribute themselves uniformly on the circle. Does that? And the bigger the rank, the faster they become uniformly distributed. Exactly right. Yes? Oh, good question. Yeah, why are elliptic curves useful in cryptography? So people probably have heard about elliptic curve cryptosystems and elliptic curve primality testing, et cetera. It's essentially because they form what's called an algebraic group, which I haven't used the term, namely this process of taking two solutions and producing a third using that secant line allows you to construct a group structure on the set of solutions. And all of the very sophisticated primality tests, Pollard's P-1 test and the P+1 tests are really using multiplication in a group. And Lenstra realized that these elliptic curves would provide other groups which would be very useful in this kind of testing and building of crypto systems. And without getting too far in advance, they've turned out to be remarkably useful. I occasionally go down to the NSA and give a talk on recent progress on elliptic curves, the National Security Agency, and whenever I say something, I hear a lot of snickering in the back because they know so much more than I do, but they can't tell me. So they're very popular with the cryptographic community. Yes. Yeah, take a mic. Why not?
Could you talk a bit about how you kind of numerically gather evidence for these conjectures? It seems very hard, for example, to find the order of vanishing of some analytic function at a point.
Yes. Well, in fact, if the function is given as an infinite product, it's almost impossible. So Birch and Dyer tried to make computation. Swinnerton and Dyer was one of the first people to work seriously at the computational lab in Cambridge and desperately tried to understand the convergence or divergence of this infinite product. It's very difficult. But if you get to this result that I pointed out was proved by, let's get back here, by Richard Taylor and Andrew Wiles. There we go, that it's a modular form. This was suspected for some time. This is an old conjecture that goes back to the work of Taniyama and the Japanese mathematicians Taniyama and Shimura, and then also André Weil. If you have that this function is a modular form, then it's not so difficult to analytically study the L function. You can write down integral expressions for it, and that gives a very quick way of computing it and also estimating its order of vanishing. So that's what Zagier and I used in our construction of a point, that we had analytic control of this function because we assumed it came from a modular form, and then a few years later, that's what Taylor and Wiles proved. Yes?
Hi, I have a question about the two ways that you introduced of tackling this question. So one is the prime number, and the other one is the height. Like, it seemed that the mathematicians came up with some strange construction of some function, and which turned out that could help us. And I'm wondering if this is common in number theory, and how do mathematicians come up with these constructions that seem
Very good, very good question.
Nowhere.
Well, for example, this infinite product that was used to define the L function, where did that come from? Well, that's analogous to infinite products that had been studied in the 19th century by Euler and Dirichlet and Riemann. And people realized they had made a successful study of those functions, which were called zeta functions, and why not try to make something analogous for cubic equations. So very frequently one has a system that works in some simpler case, and one says, well, maybe it would be sensible to try to generalize it to this case. And so it's frequently arguing by analogy, and also this summing up all the cubic equations of height less than x. Well, that had been done in other situations, not for cubic equations, but for quadratic fields or for cubic fields. And people, again, just tried to make an analogous situation and see what would work. And many times you make the analogy and it doesn't work at all. And again, the computer was an enormous guide in this case that indicated to them that they were onto something very quickly.
I was somehow interested in the problem of the finiteness of the rank. So here is my question. So suppose that the conjecture by Birch and Dyer were true, then we would know that the order of vanishing would be equal to the rank.
Yes.
So my question is the following. So is somehow easier to control the order of vanishing of the L function than actually controlling the rank? So in other terms,
yes,
would that
it's much easier.
help us answer the fineness of the rank question? Thank you.
Well, you'd have to prove the whole conjecture, but if you said to me, here's a cubic equation, what would you rather do? Determine the rank of the number of solutions, which is something that we have a way of dealing with, or would you rather compute the L function and compute its order of vanishing? You would always compute the L function and its order of vanishing. It's amazing how quickly that goes. But we don't know how to prove the equality of the two things, so we have to go with the original proof that the rank is finite, which uses a lot of beautiful number theory too. So I wouldn't want to eliminate that proof, but if you asked what is easier to study, it's what's called the analytic rank, namely the order of vanishing of the L function turns out to be the easiest thing to study. Sure.
My question is about the L function. So beyond 2/3, it looks very smooth, but how come you cannot find a way other than the infinite series to represent it?
As I say, eventually they did find a way to represent it, but very many times in mathematics, functions are defined by an infinite process, and as I said, this is the simplest example of just this infinite sum of powers of x, where the initial definition may not be the right one. And what Euler discovered was there was a better definition where it was defined in a larger domain. And that's what this modular form does. It allows us to define the L function in a larger domain than its original definition. Okay.
And do you think the extension or the continuation to the left of 2/3 would tell us something about?
Yes, I mean, we've only studied it so far at the point where s is equal to 1, but it also seems extremely interesting to study it at all the negative integers, s equals 0, s equal -1, s equal -2. So you want the full continuation, not just to a neighborhood of 1.
Or it could be just a continuation of series, but unrelated to
Could be.
the problem.
But in this case, the continuation is very useful for the problem. Is there?
She wants to know what's a modular form.
Oh, that's too much to ask. It's a function on the upper half plane, and so it's a function of a complex variable, but only a complex variable on the upper half plane that has a certain invariance property for an action on the upper half plane. It's a beautiful subject which no one really understood was connected to elliptic curves at all. Well, it was connected to some properties, but not the number of solutions of elliptic curves. So that was an amazing connection that was made by, as I said, Taniyama, Shimura, and Vey as a conjecture that sat open for 30 years. But that's a whole subject, so you'll want to take courses in the graduate department of Stanford mathematics to go on, learn about that.